So welcome to the course MGM. Today's topic will be variational autoencoders, and this forms the foundation of explicit models, which will give us a way to go to variational diffusion models and so on. So let us look into variational autoencoder. So in short, it's called VAE. So just a quick recall about probability measures. So given a set of probability distributions P on a random variable x, divergence is defined as, so we have seen this couple of times already. The probability measures that we define is a way to compare between two distributions. So we have the popular one we have seen is scale divergence, which is written like this. And so in general, I still say that D is some divergence. So let us not bring K divergence right now. So what we expect in general is that divergence between P and Q is always positive or non-negative, where P and Q are some distributions, and P divergence between P and Q is 0 if and only if P is equal to Q. So these are the interesting properties that we expect from a divergence, the basic necessity. It may not be a metric because, for instance, scale divergence is a divergence, but it's not a metric because it does not satisfy the symmetry property and the triangle inequality. Okay. So in general, what we know is that divergence is weaker than distance. By distance, we mean metric. Okay, so for instance, the usual norms that we see, L2 norm. Okay, so that's a metric. So in general, divergence are not a proper distance. So basically, it does not satisfy symmetry or triangle inequality. So these are the basic facts, and so this is the recall on the distance divergence measures, and then we have a quick introduction to just the basic notions of probabilistic graphical models. It's a big topic in itself, but our goal will be to just have a basic notions. So usually a probabilistic model, you can define it using graph. Just like in any problem, you use graph to model more complex problems. So in this case, if your model is based on probability, where there are independence between two random variables, then you may want to denote it as a graph to show which variables depend on which and so on. So a basic idea is define model. So in this case, model could be your problem. So define model as distribution on a set of random variables with particular dependency. Okay, so we will say, like, depending on the problem at hand. In fact, VAE will be one such example where we will see one application of a graphical model. So in this, many things can happen. For instance, in this model, some variables may be unobserved. So PGM, or in short we call it PGM, okay, probabilistic graphical models, PGM. So in general, PGM are powerful models that use graph to describe dependency. So graphical models, as I said, is a big chapter in itself. So a reference for this would be chapter, I believe, 8 of the Bishop's book. But as I said, in our case, it won't be used in a very deeper way. For us, it will be a modeling, just a modeling problem. We will see how latent variables and all this are indicated via graphical models. So as I said, graphical model is a separate intense topic in itself. Our goal in this will be essentially just to know how to read joint distributions. So we want to know, for our purpose, how to read joint distributions from a DAG. So DAG here is directed acyclic graph. Okay, so DAG is directed acyclic graph. The acyclic graph is a graph that has no cycles, and directed here means the edges are directed. So let us see, we are interested in some joint distribution. So let us say we are interested in some joint distribution P x1, x2, xd, okay, for a DAG with nodes x1, x2, xd, and we are assuming there are directed edges between them, and these edges are determined by the problem at hand. So, and directed edges between them, then in that case we can define the joint distribution using conditional distributions basically, and the condition depends on the arrow, okay, where the arrow is coming from. So first let me write down the definition of how to compute, and this is product of I equal 1 to d xi given PA xi, okay, where PA is in the is one of these x1 to xd, where PA stands for parent of xi. So where PA of xi is in one of those x1, x2, xd. So PA can be multiple, a node can have multiple parents. So that's why we are saying subset. And so these represent parent nodes of xi. in the DAG. And in the DAG, we expect that there will be a root node, and root node will be a node which has no parents. So for a DAG, there exist root nodes, okay, multiple also, with no parents. Okay, obviously a root node will have no parents. So parents of xi, there exists such one of the xi for whose parents will be empty, and those will be root nodes. So let us see some example. Now we have defined some framework to model a problem via probabilistic graphical models. So if we look into some examples, then I can have a model like this. Okay, so that's a DAG. There are no cycles and there are directed edges. So this is one example. We can have another example, Z, Y, X, and the edges are like this. We can have third example, Z1, Z2, X1, X2. Okay. So the idea behind these graphical models is a way to let you plan the dependence or independence in your model. Now for this, we will try to compute the joint distribution that's written there. So in this case, I have two random variables, Z and X, and I may want to kind of compute a joint distribution here. Here I have X, Y, Z. Here I have Z1, Z2, X1, X2. So in this case, I will compute the joint distribution Pxz, and I will use the formula there. So it says that it's product of, so it's written using the chain rule. So where we apply the conditional. So that's kind of very generic way to now write things. So probability of x comma z, the joint, will be probability of, now we will look into the model, what is the dependency they have. So I know that x comes from z. So it's probability of x given z. Okay. So probability of x given z, and then since I goes from 1 to d, right? So in this case, the nodes in the DAG are x and z. Okay, and I have to do that product for I equals to 1 to d. So the first thing I did was I took an x, and then I looked at the parent of x, and I found that the parent of x was z. So hence it became x given z. And I do it for other variables now. Now I go to z. So it will be probability of z given parent of z, but parent of z is empty. So it will just remain probability of z. Okay. So the second term will be probability of z, and it was supposed to be conditional with parent of z, but parent of z is empty. So that condition, putting that condition has no use, so it's not really a conditional. So we just write like this, probability of z. So this corresponds to the first graph, which is, let us say, A. So for A we have this, and similarly we can work out for B. So now B, again we are interested in computing the joint distribution. So here we have probability of x, y, z. Now this, again, we run it through the product I equal 1 to d. So in this case, let us say x1 is x, x2 is y, x3 is d. So then we will write probability of x given the parents of x. So probability of x given now the parents of x are z and y. So we put that here. Since we are using x, y, z, so it doesn't matter. I write y, z or x, z, y. It doesn't matter. But let us keep the ordering. So then, so that's the first term. I equals to 1, I'm done. And then I will go for I equal to 2. For I equal to 2, the variable is y. So this is probability of y and parent of y. So parent of y is empty. So this is just probability of y. And similarly, parent of z, similarly probability of z and conditional on parent of z. Parent of z is again phi. So it just stays at probability of z. Okay. Similarly, we can work out c. So here we have 4 variables, x1, x2, z1, z2. So then we have probability of x1 given parents of x1. So parents of x1 are z1 and z2, okay, because these arrows are coming from z1, this arrow is coming from z2. So the parent of x1 is z1, z2. Then I look at the other variable x2. So probability of x2 and parent of x2 is z2. So this is probability of x2 and parent of x2 is z2. Then I look at the third variable, which is z1. So probability of z1 and parent of z1 is none, empty. So it's just probability of z1. Similarly, I have probability of z2. Okay. So this is a basic idea about probabilistic models, where if your problem is based on probability models, then this is one way to visualize your problem and do computations and look at dependencies. Yeah, Z2 has a parent, sorry. Okay, so thanks for this. So Z2 has a parent, so and the parent is Z1. Okay, thanks. And P of Z1 again, right? Yeah. Okay, because we have to run the product for each xi. Okay, so yeah, one second. We have to go with that, right? So probability of Z1 we already did, right? So I don't have to go for probability of Z1 again, right? Because Z1 I already calculated, right? We just follow this, right? So basically in this product, what you're supposed to do is, let us write this product, because then it will explain whether repetitions are allowed or not, right? So the way we do this is, in this case, let us say, right? So I write list x1, parent of x1, x2, parent of x2, x3, parent of x3, x4, parent of x4. Okay. So this is what we are supposed to do. So in our case, x1 is x1, x2 is x2, x3 is z1, and x4 is z2. Okay. So x1 is our x1 and parents of x1 are z1, z2. So that's covered. Then we go here, x2 and parents of x2. So x2 given z2, that is covered. Okay, so we just have to like tick this. And then x3. So x3 in our case is z1 and parent of this. So that is covered like this. And then we go to x4, and x4 is this one and parent of this. Okay, so as I said, It is enough that we circle. Basically, what you have to look for is this: are these guys covered? Okay. Once they are covered, they are not kind of they are not supposed to be repeated. Okay. So in this case, 4. So this way we can construct quite complicated models, and for VAE it will be a very simple one. So this is VAE, the simplest DAG that you can think of. It's a latent variable model, so kind of JAD is not really observed, but we will figure out a way. And this is conditional VAE. So I will generate the images, but also with some condition on the images. Okay, we will see that. Okay, so we can create images based on some additional characterization of the image. So this gives us a kind of a generic way to think about the problem, and obviously write down these things. And as you will see, for VAE we just use this. So this will be our starting point to derive VAE, but obviously that is not enough, because the problem is that the latent variables, working with latent variables is not straightforward, right? Because if I have to integrate over the JAD, the JAD is not really known, right? So that's why that's where all the trick goes into computing lower bounds and so on, and that's the whole point of today's class. So example A relates to VAE and GAN, so that's the model for those. Yes, it's also one of the, yeah. So if you go study probabilistic machine learning, then there are many, like there is a lot of topics based on graphical models. So if you go to the Bishop's book, there is one chapter on hidden Markov models as well. So that's why PGM forms a very basic framework on which you can. There are also undirected models. Okay, so some of these will go into undirected, some of these will go into directed. So in general, when I talk about graphical models, and then you have directed, undirected. So some variables are observed, some variables are not observed. So JAD will be latent, let's say. Then it's not observed, but I use this as an intermediate feature extractor to kind of get some interesting information via JAD, and then so one application of this latent variable model is VAE. That's what we are. So example A corresponds to is a latent, and I will explain what is latent here. Basically not observed. Okay, so and is a latent variable model, and we use this in VAE. So as I said, this is what we will start with, A. And if we look into example B, then it is example B is a latent variable model. So latent variable model is also called LVM. Used in VAE, conditional VAE. I mean conditional. I have not done conditional GAN, but there is a conditional GAN as well, so you can do that as a project. Okay, so and so where Y represents additional information, okay. So this is a very brief about probabilistic graphical models, and we are aware of the Jensen's inequality. I will just quickly write down these two. We will use this, and a generalized Jensen's inequality also will be used. So I will quickly recall this. So recall so Jensen's inequality told us expectation of Px Fx is greater than or equal to f of expectation of Px Fx. Sorry, x. So this is what we have used a couple of times already. So the average of the function is greater than or equal to function of the average, and equality holds if f is linear. And one of the other things we know, so this is, let us say, P1. One of the other things we know is the result called lotus from the probability. Basically, it's used to compute expectation of function of a variable. Okay, so this is also, we just recall it. So given distribution Pxx and a function y equals to g of x, such that expectation of P of xx g of x is less than infinity, and random variable y equals to g of x has distribution, let us say Pyy, then expectation of Py y y is expectation of Px x g of x. So lotus is a result that we have already seen before. So if I have to compute expectation of a function of a random variable, then I can just do expectation with the over the distribution of the x itself, but then the values I compute are g of x. So this we have already seen before. So now we will write generalized Jensen's inequality. So if a function f or gx, let us say gx maps inputs to scalar outputs in R, and f from R to R is a convex function, then for any distribution Pxx, we can write expectation of Pxx f of g of x is greater than or equal to f of expectation of Pxx gx. So what we have seen here is it's a generalization of the Jensen's inequality, and the generalization here is coming from the fact that we have any function g, but then it's composed with a convex function. Okay, so if a function g, which is a scalar valued function, if it's composed with a convex function f, then also this inequality holds. Okay, so this is why it's called generalized Jensen's inequality, and we may try to prove this. So let us compute expectation of Px x and f of g of x. So this is expectation of Py and f of y. So I want to compute expectation of f of g of x, but then g of x, I can call it another random variable y, and I assume that y has some itself has one probability distribution Pyy, so it translates to this. And now this is now since f is convex, using Jensen's inequality, I have that this is greater than equal to, so this is Jensen's, and the fact that f is convex. So this is f of expectation of Py y, okay. So this is just Jensen's inequality on f, and now basically we substitute things back. So this is equal to f of expectation of Px x gx. Okay, so we applied the lotus back. Basically we substituted y again to be g of x. So this is what we were supposed to prove. And then we have been working with KL divergence for quite some time now, so there is not much to recall that now. So just the basic facts that KL of PQ is greater than or equal to 0. So these are the things you can check by yourself. These are the basic facts we are trying to recall, and equality holds if P equals to Q, and then minimizing KL divergence is equivalent to MLE estimate. Okay, so these are the proofs we have done before, and it's good to recall this because we will be working with explicit model, and in explicit model we will work with the probability distribution itself. Okay, so in fact our starting point will be the form of the MLE estimate itself, rather than the KL divergence we used when deriving GAN. Okay, so it will be clear soon. So without deriving this, because I have derived this already, but just to bring in the notations we had. So let us say I want to kind of do some argmin of KL where P data, and then I compare with P theta x, some distribution, but we know that P theta is something that we try to generate, right? So essentially I want to minimize these distributions. Then we have proved this. In fact, this was also in the midsem exam, is that this theta star is same as argmin of 1 by n log of P theta xn. So if I am given n samples, then this is same as, and I have made a small mistake because this is maximum likelihood. So the likelihood, we maximize the probabilities, right, for the given xn. So what we have seen is that minimizing KL divergence is equivalent to doing the MLE estimate, and we call it estimate because now it is being computed on n samples, and we are trying to maximize the probability. Okay, and this is your template probability distribution, obviously. So in MLE estimate, which template you use, that's your. We saw in probability class we saw a example of a red ball and blue ball, and we choose a distribution template there which was binomial. Okay, and then so this depends. In our case, like you will see that we make it even a neural network in some sense. Okay, I mean parameterized by neural network. Of course, distribution is not the neural network, but it is parameterized by that, meaning that the parameters of the probability distribution. So if it's a normal distribution, the parameters are mu and sigma. So basically, learning the distribution with mu and sigma is essentially like I am saying, is there a neural network which, based on the samples, and the neural network has some parameter, it can predict me the theta, mu theta values, and it can also predict me sigma theta values. Okay, so this is the kind of parameterization we do, because neural networks are very powerful in learning. Okay, so then these are the things we do, where in fact this is exactly what we are supposed to do in today's class. So minimizing K divergence is same as doing maximum likelihood estimation. Okay, so that's, we have done this. So this is the second time we are trying to understand this. Now let us go to now the variational inference part. So this is just a recall. I believe there are a few things like generalized Jensen inequality, probabilistic graphical model, and so on. So we have everything set up now. Now we'll go to variational inference. We will start with the example A of probability, the graphical model where you had Z pointing to X, and VAE is based on that. Okay, so let us try to compute the joint distribution there for the VAE. So we are interested in so variational inference, and we are interested in the latent variable models, which so yeah, let us start from the variational model itself. So recall, what was that? Z, and it's give me X. So let us work with this model, and then we had the joint given by is probability of X given Z, probability of Z. Okay, and my goal is to learn Px, right? And what I know is the joint. So of course I know that I have to marginalize the joint with respect to Z. Okay, so what we know is that probability of, if I have to compute probability of X from the joint, then I have to integrate out with the Z. Okay, that's what we know. So this is from the joint we get the marginal. And our goal is to indeed get probability distribution with X, but the Z is the major bottleneck here. Z in the sense we are bringing Z for a reason that it will understand it will extract some interesting features, and it will also help in the generation later on. So we will see this encoder decoder form. So Z in the bottleneck layer is indeed the one that's doing the encoding for us. So we will get there, but the point here is Z is indeed a bottleneck, because while computing this integral, now I will substitute this integral by this part, because this is equal to this. So basically VAE starts from here. Okay, so now if I have to write in one line, then we are interested in the latent variable model, which is given by, so I use some theta as a parameter. Obviously I have to specify this a bit later, but so it is some p theta x given Z, and for the moment you can forget about the theta. Okay, but this will evolve as we derive this. So our starting point is this, and in the starting point what we say is that this is not tractable integral. Okay, so the whole trick will go into making this integral tractable. And one of the way what we will do is that we will identify a lower bound. So basically we will go for a trade-off in some sense, that we will work with something tractable but not exactly the same. It will be some kind of a lower bound of this, and that we can estimate. Okay, so our next step will be to find a lower bound of this. To spill the beans a little bit, I can already say that although it will not make too much sense right now for you. So if I have to build a deep generative model, okay, so as I said, don't think about this right now. I will just write it, and then whole point will be to explain this. So in deep generative models, what we do is we will assume some template distribution. So in this case, let us say this one choice of probability distribution, and my another choice is okay. So since I am using g theta small throughout, so let us use this. Okay. So as I said, as such, you cannot you have to use some template. Okay, so in this case, let us say that you use some template distribution which is normal. In this case, it's standard normal, and this is the usual normal, not standard in the sense that this is mean is not 0 and variance is sigma square entity. This is a multi-dimensional one. That's why you see the matrices being applied here. Okay, but all have kind of like same variance sigma square because it sits on the diagonal, and this is a vector of the means. Okay, because x is multidimensional, so x is a random vector, mean should be a random vector, and sigma square will be a matrix, I mean in this case. So but as I said, I have just put this but without really telling you what we are supposed to do. So we will come back to this a bit later. And g theta x, just now I gave you a hint that we use some neural network to estimate these means. Okay, so it is a neural network obviously parameterized by theta. Okay, so as I said, don't think too much about this right now. Let us go back to this. Okay, so let us give it name star here. And as I said, the star is developing star is intractable, integrating is intractable. So integrating star is intractable. So what should you do is develop a key idea develop a lower bound that approximates log of p theta x. The reason why we put the log here, it's again is coming from the fact that it was like a log maximum likelihood estimate and so on, right? So whether we estimate p theta or the log of p theta, which is also which shows up in MLE estimate, so it's fine. Essentially what I'm saying is this integral is intractable and we need a lower bound, which at least I can work with the lower bound. So now let us do the derivation of the lower bound that I can use, I guess, this one. So now let us start with the log. Okay, let us start with estimating log of p theta x. So this is log of that integral, which is p theta x given z p z dz. Now what we will do as a first trick is something called importance sampling, and the idea here is that you introduce a new distribution that you feel that you can sample from easily. Okay, so let us see what it means. So it is log of qz and p theta x given z pz and divided by qz. So as you can see, I have artificially introduced a new random variable qz and qz. They get cancelled out and I get the same term above. But the idea behind this kind of trick is that qz is a distribution that I feel comfortable working with. Okay, so then it will be a little bit clear later on what will be the role of q. So this is a usual trick, and the name goes by importance sampling. Okay, so then now I will use generalized Jensen's inequality. So and the Jensen's inequality will apply on some convex function, right? So the function that is convex is the log function, right? In fact, it is a concave, so the inequality I believe will be the other way. So Jensen's applies on both convex and concave, because the negative of the concave is convex, so you can always work on concave also. So given that log is concave, applying, and this is like generalized Jensen's inequality. So when you apply on concave, just that the inequality changes. Okay, if it was less than, then it becomes greater than. That's it. So generalized Jensen's inequality. So from that we have this greater than equal to, and obviously we are taking the we will be taking the log inside. Okay, so the way we see this is, I wrote this in terms of expectation, right? So if you want, I will do this additional step if it seems that it's a little bit. So let me write this as an expectation first. So this is log of expectation of this guy, and expectation is taken over this. So this is expectation over qz of p theta x given z pz divided by qz. Okay, so I just did one more step so that you see that Jensen's was applied on the expectation. So it's like function of the average, okay, will be greater than equal to average of the function. Okay, so basically it will be greater than equal to when expectation comes out now. So that's the generalized Jensen's inequality. So from Jensen's inequality, so this is the generalized Jensen's, and some people call it Jensen, and I prefer call it Jensen because I believe it's a Denmark name of the person from Denmark, and there they pronounce J as Y. Okay, so I think it's proper to say Jensen's and Jensen's. Okay, so we bring the expectation out, and from the generalized Jensen's inequality we will get a greater than equal to sign. So this is again, like, if you want, I can write this as in terms of expectations first, and then write the expectation as an integral later. So this is expectation of log of p theta x given z pz by qz dz. I mean, not dz, we are not doing integral right now. So this is what we did. We bring log is concave, we bring this, then we get a greater than equal to sign, and then now we go back to the integral. So expectation, we believe these are continuous distributions, so we will bring in the integral. So this is integral of qz log of p theta x given z pz by qz. Okay, okay. Yeah, it's concave, so it will be other way. Okay. Jensen's was for convex. For concave, as I said, the inequality just flips the other way. Okay. Okay. So then let us do some rearrangement of these terms. And often what happens is that when I am doing rearrangements, I am looking for the KL divergence. Okay. So let us do that. So this is expectation of qz log of p theta x given z minus kl qz pz. Okay, so I did a rearrangement here. As you can see, log property of the log I have used, and I have used the fact that, so if you want to see the KL and the rest, right? So let me figure out the KL. I will mark it as in circles, and the remaining you will figure out. So KL goes with this and this. Okay, so the KL term was qz, and then because qz is the bottom, so I did a change. Then I got the negative as well. Okay, and then so to derive this as an additional step, let us do this. So this, I will break this as qz log of p theta x given z, and because this is a log, so this is this, and then plus log of this by this, so plus qz log of pz by qz. Okay, so overall from here to here we get this, and then I did a reversal of sign by taking a moving them up, because I am looking for KL divergence. In KL divergence I have q on the numerator, so to make it KL divergence we flip this, so q becomes p and p becomes q, and the cost for this is that this will now become negative. Okay, and now you can easily see that this guy is the expectation term, this guy, and this guy is the KL divergence term. Okay, so and we can make a new notation for this difference. Okay, so this difference I call it, let us say, L x q theta. Okay, and this difference is essentially going to tell me, or try to understand what this how this lower bound will be. Okay, so now let us look into this LQ theta term. So remember that QZ was the one introduced via so-called information importance sampling. Okay, so that's something we have to figure out. Okay, what would be a good one, and from the base theorem. So basically we will go further on this. So from the base theorem, what we have is p theta z given x is p theta x given z pz divided by p theta x. Now if we substitute this, or let us first look into the difference of the maximum likelihood term and the KL divergence, and from there we will relate to L. Okay. So now let us look into this term, log of p theta x minus KL qz p theta z given x. So this is log of p theta x minus, and this we can expand the definition by KL divergence, log of qz by p theta z given x. So basically we have used the base theorem here, p theta of z given x, and we so p theta z given x. I think I have jumped one step. No, okay, I have not jumped any step. It's fine. Okay, so far it's fine. What I'm supposed to do is next substitute this as a next step. Okay, so that's fine. So log of p theta x minus, I can substitute this p theta z given x. That's why I wrote this in the first line, in this expectation term there in the second term, and see what happens. Okay, so let us do this step. So I will substitute this from here. So this is expectation of qz log of qz p theta x divided by p theta x given z and pz. So what I have done, I have substituted this p theta z given x as p theta x given z pz, and then p theta x went up. Okay, so now let us see what it leads to. Look into this term, expectation of log will make it into sum, right? So this will be log of qz plus log of p theta x, but then p theta has nothing to do with this q, so this will be like a constant. So the expectation qz of p theta x, log of p theta x will be log of p theta x. So these guys get cancelled. Okay, so that will be the next step. So this is equal to log of p theta x minus expectation of qx p theta x minus expectation of this qz and log of qz by pz plus expectation of qz log of p theta x given z. Okay, so I have basically expanded this log term. So if you see the first term was log p theta x already there, and then I extracted this expectation of qz log of p theta x, so that came as this term, and then minus expectation of qz qz by pz. So this is log of qz by pz. I take that as a second term, and then the third term is log of p theta, and this is the negative log of p theta x given z. So negative becomes positive. So this is positive of log of p theta x given z. Okay, so with this we can write this as expectation of qz log of p theta x given z. So and then so I have picked basically this term as a first term, and then basically so these guys get cancelled because this is expectation of p theta x, as I said, with respect to q is a constant, and there is a log here. Okay, so it's the same thing. expectation of a constant is the same thing, so they get cancelled. So we are left with this. So this is KL between Q and P. So this is minus of KL, QZ and PZ. So what we say from here is this implies log of P theta x minus L x q theta is nothing but KL of QZ given P theta z given x. So this will help me kind of look into these lower bounds that we are suggesting, because KL divergence is always greater than or equal to 0. Okay, so what it means is that L cannot exceed this term. So it means that maximizing this lower bound is a good idea, and I cannot overshoot it because this is supposed to be greater than or equal to 0. So this is always going to be less than or equal to this, and if I kind of maximize it as much as possible, and if it is possible that it matches this, then this is exactly the place where the KL divergence will be 0. Okay, so so then I will write this, what I have said just now, I will just write down in words. So in words I will write down as, since log of P theta x given z is constant with respect to q, maximizing L x q theta is equivalent to minimizing KL QZ of P theta z given x. So as such, we are supposed to maximize the L, and if we maximize the L, then more we maximize the L, lesser the KL divergence will be. Okay, that's the motivation behind having this lower bound and then trying to maximize this. So so then we, with this lower bound in hand, we will try to build now the variational autoencoder. So far what we did is derive this lower bound here. Okay, so as I said, the fact that KL is greater than or equal to 0, we always have that L x q theta is less than or equal to log of P theta x. So that's guaranteed, since KL is greater than or equal to 0. So let us give it a name. This is let us say double star. So from double star, and this Q is the one that you introduced in when you did importance sampling. So you feel that Q is something that is tractable. Okay, so the variational autoencoder paper, they will choose Q to be of some form. Okay, so for VAE, where it was proposed in the paper by Kingma and Welling, and this was proposed in 2014. So the choice of Q decides the formulations for VAE, and the choice of Q was Q phi z given x. So there is a nice picture for this, but before that let us first work out this. So QZ is taken as Q phi z given x. this is the substitution choice of Q that's taken, and with this, yeah, we will kind of figure out the full algorithm for VAE. But so, and then moreover, as I said, when you do such choices, you have to kind of, for practical algorithm, you have to choose some template distribution. So in this case, he chooses normal distribution. Okay, so here I will also say what type of distribution Q will be. So Q will be with the choice of Q phi. So phi, again, you can think of this as some parameterized network, and he chooses to be Z mu phi x and diag of sigma phi squared x. And where mu phi x and log of sigma phi x is given by some neural network parameterized by theta. Okay, so this is the choice of the Q, and more precisely, so Q is given as a conditional, okay, on x, and more precisely, it's taken to be a normal distribution with mean mu and variance sigma phi squared. And this mean and variance are parameterized by a neural network, in the sense that looking at the data x, it will try to predict the mean and the variance. So let me define the VAE objective, and then I will draw a small diagram, because diagram will help here. Okay, what is going on, because you are seeing, usually you are seeing x given z and z given x, and then you see theta parameterizing x given z and phi parameterizing z given x. So all this is giving you a way to see that there is some encoding being done for x, which becomes z, and there is some kind of decoding being done after getting z. We are trying to retrieve x. Okay, so this is the picture we have in mind, but I will come to that. So in general, now with this framework, with this lower bound idea in mind, and with the fact that the choice of Q is taken like this, and moreover like a normal distribution, now we can write the cost function, right? So as I said, in any problem we have modeling and solver. We are doing the modeling of a problem. So now modeling will lead to some optimization problem in min max. So we are at that stage that now we will write the optimization problem. So define VAE objective as phi star theta star is argmax over L phi theta. So the question is it argmax over both phi and theta, or okay? So basically you have to look into the double star, right? So double star tells me that L x q theta is log p theta x minus the KL. Okay, so since p theta x is the maximum likelihood estimation, I always want to maximize. So this is maximized with theta, and KL divergence I do a minimize, but that KL divergence is with the minus. So essentially it will boil down to maximize again. Okay, so it will be all max, okay, over theta and phi of this L term. Okay, so it is good that I also write the L term as log of p theta x minus KL of q z p theta z given x. So remember that q z is now replaced by q phi z given x. So maybe for the VAE, it's a good idea to kind of it's a good idea that I separately write that for the VA, because this is just a template for the moment. Okay, you see this as a template. Now what choices of Q and all this I do will determine the loss function. So for the VAE we said this. Okay, so with this, where L phi theta is defined as expectation over Q phi z given x of log of p theta x given z, and then minus KL of Q phi z given x pz. Okay, so all this has to be computed over the distribution p theta x, because the x are coming from here. Okay, so overall this is what we have. So in general, these losses will be calculated over some samples. Okay, x and the latent variable z. So overall you will get some kind of an average estimate. Okay, so you are supposed to take expectations on these. Okay, so so what we did is that we replaced Q z. Okay, so it seems somewhere I might have done some mistake. Okay, one second. If I look until the line just above the double star, there, until there, it seems okay, because then, oh, okay, so this is the difference we are taking, right? X given z, and then KL of Q phi z given x and pz, right? And yeah, this was our LXQ. Okay, right. I believe what I did is I think I'm missing the first line from there. Okay, so what I can do is maybe I have to do some corrections, because until here things are relating well, and this was where I did I looked into the log of p theta minus KL, which came from the previous step. So we further extended that, and that was our, so basically this guy was our LXQ theta. Okay, so we had this LXQ theta, which was difference of this. So this guy is LXQ theta. Okay, so let me kind of maybe there was something missing here that I, so what we want to track is that this was our LXQ theta. Okay, so in fact, so just before this step we did this lower bound LXQ theta, and then we said that then LXQ theta was equal to the difference of this. Okay, and then we went ahead and we wrote it like this. Okay, so this is the LXQ theta is this. Now look here. Okay, so LXQ theta, and then what VAE says is that replace Q by QZ by Q phi z given x. Okay, so then if I replace that, so QZ by Q phi z given x, so I replace QZ by Q phi z given x, and then expectation QZ I replace by expectation of Q phi z given x, and everything else is same. Okay, so that relates directly from there. The double star that I wrote was a little bit doubtful. Okay, the notations were not very, so but from here we have and we calculate all this over all the data we have on X. Okay, so this is the VAE objective. Okay, this is the optimization problem we are going to solve. Until here, it's you arrived at some lower bound, and then different choices of Q can lead to different methods. And what VAE suggested is that let us go for this choice, which essentially resembles like encoder decoder form, and then your objective becomes this with all this. So of course you may say that how am I supposed to compute expectation of Q phi z given X and so on. So that's the whole point we will develop today. It may go beyond the class timing today, but that's the whole idea. Okay, so until here we are all in sync. We derived a lower bound. From the lower bound we had a choice of Q to be made. Q was the important sampling term, and that's the trick usually they do, where you have a view in mind that later on kind of like I will replace Q with something that I want to work with. Okay, so then we arrive here. Okay, so until here everything is okay, and now the question is, okay, this is the modeling part. Now after having a modeling, how will you go about solving this optimization problem, right? And since this is a, as I said, these guys will now come in picture. These are the templates that I have in mind. So I have to now work with the Gaussians. Okay, so that's why we did some work with the Gaussians. So we have to see what is scale divergence when this is some Gaussian with mean this and C. Okay, so we have to calculate this now. So in some cases you have a closed form formula like KL divergence. We can compute some explicit closed form expressions for KL divergence. In some cases it will be estimate. So these are the two things we are supposed to do going forward. Now to give you a basic idea of, because there is so many things happening here, right? Which one? Yeah, phi is also parameter neural network. Phi and theta both. Okay, so let me give you a small diagram just to explain what you asked just now. Okay, because these things may look a little bit. So I will do this diagram again as a conclusion later on, but VAE follows kind of this. So the VAE model tells you is that you take samples X, okay, and you generate some random variable. So basically these are neural network. Okay, so basically neural network are nothing but just a function, okay, of some theta, let us say. Okay, so X goes in and something some calculations are done on X, and the parameters of the model are theta. So this is our theta. Okay, and then based on this, now these guys, since this is a probabilistic model, I say that generate mean like this and generate variance like this. Okay, so this neural network, because this is a probability model, I'm not looking essentially, I mean I'm looking for the parameters of the distribution itself to be generated. Okay, so it gives me this. So basically it defines the X goes in, it tries to learn a distribution for the X. Okay, so this is somewhere Z is sitting somewhere here, and so this is your Z given X. Z given X is this guy. Okay, so Z given X is, so this is your X, this is your Z. Okay, so this is your Z given X, and then the VAE says is, so this is your encoder form. Okay, so you are trying to encode, and then you will retrieve X given Z. Okay, and both are models trying to learn the distribution. Okay, unlike GANs. Okay, GANs may be learning distributions implicitly, that it never reveals to you, but here you want to explicitly go via distribution estimations here. So I learned some distribution, and I'm telling in advance that of course there are many distributions in this world, right? So you have to choose certain hypothesis class for your model. So in this case we say these are class of normal distributions, and with mu and sigma. So generate that for me, and then from this distribution I would like to retrieve my x back. Okay, so basically what it will produce is x hat later on. So this is also some parameter phi. Okay, so the way things are, it's the other way. So this goes with phi and this goes with theta. Okay, so as you can see we have p theta x given z. So we have this, and this is our phi. So phi is the neural network parameter that tries to do the encoding for us, and this encoding is essentially trying to produce the mean and the variance. Okay, and for many data it will try to do this, but then the problem is that will you allow it to just kind of produce anything arbitrary? Okay, so that's where the KL divergence comes in picture. KL divergence tells that okay, you encode the model as normal distribution with mean and this, but then I don't want you to generate things arbitrarily even within the normal distribution framework. I want you to be close to some distributions that I am familiar with, which is, let us say, normal. Okay, so KL divergence is telling me that you generate some distribution here, and I want a base distribution z, and I don't want you to go out of, like, I don't want you to just generate arbitrary things, because in the usual normal distribution you cannot sample unless mu and theta sigma is known to you. Okay, so the things that are known, even for sampling, you need distributions whose parameters are known, uniform or standard normal. Okay, so we need distributions from where I can sample. So if it always gives me something arbitrary, because for each sample it may give different mu, and it's not easy for us to sample from there, because it may not be easy for us to predict, identify the mu and sigma from there as a fixed quantity. So we say that okay, you generate this, but then I force you to be close to the standard normal. Okay, and then there is something called reparameterization trick. We will do that. So then, for this right now, I will say that it does that, and then from there, these samples that you generated with this mean and u are perturbed by some epsilon noise, and then it goes in, and then I check for the reconstruction error, which is x minus x hat, where x hat itself will be given by some g theta z, where z is this that came from here plus the noise that I had. So that went through the neural network, which is g theta, and then I am saying that this x hat that you are predicting now should be close to the x that I had. So what I said just now is still there are some details to be filled. So let us work further to fill the details. Okay, so this is the picture you can have in mind. In the model, what it is trying to do is that it's trying to learn a distribution z given x, and then it's trying to retrieve x from the z. Okay, and the very important key idea is this so-called reparameterization trick. So we will do that, because if you don't do that, it just remains a usual encoder decoder. Okay, the reason why you inject a noise, and this noise will be used in the generator, because in generator you will use this. the fact that you are allowed to use the injector noise here, it gives you the variations in the data you generate. Okay, so we will look into this in detail. So for the moment, just forget what I said just now. Let us work with this. Okay, and we will figure out everything. So what is to be figured out right now is how do I solve this? And even if I have decided in advance that these are going to be some normal distributions, I need some way, computational way to calculate these. So this will be our focus now. So first, I believe I will find the closed form for the KL divergence. So let us establish this, because there is a KL divergence for normal distributions. There are like known closed form solutions. So there we can kind of write that explicitly. So the fact that these guys are known, it helps me to sample. So compared to the usual autoencoder, in variational autoencoder, we are looking for generative task, and in generative task, we want a way to sample from a known distribution. So forcing this guy to be close to this is helping me build a generator which can legally be sampled from normal, because these guys are forced to be mapped to normal. So when I will take standard normal from next time, I will know that there is a good representation from X to that, and from there I can generate. Okay. So in fact, this is the key idea of the variational autoencoder compared to the autoencoder. So okay, so let us build on this. So I said some remark about reparameterization trick, because the reparameterization trick is a way to kind of generate from the standard normal, but then since you have created this mu and sigma, you want to relate it to the standard normal. So you do this reparameterization trick where I take samples from this, and I know that I can generate I can generate a vector normal distribution mu and sigma. We have done this in the probability class with a base as a standard normal. Okay, so with a base standard normal, I can do a proper shifting where X will become sigma z plus mu. Then if you do this scaling and shifting, so if you ask me to give me a sample with mean, mu and sigma, then I will generate it from the normal and then say take it like this. And this was not just to be able to write like this, but also because I wanted to go here. Okay, I know that for some of you it will be still very high level, but it's just you can think of this as a plan that we will explicitly like derive. So the point here is that by doing this, I also have access to this, because if you just leave it there, and if you do a stochastic sampling from there, that's a stochastic sampling. Stochastic sampling does not allow you to go and fetch the phi, go and tune the phi of your parameter of your model, because stochastic sampling does not give you this picture of sigma phi and mu phi, so that I will do backprop until that. Okay, so this was an important step, because then I will also go with this. I have access to sigma phi, mu phi, rather than saying that just generate something out of the normal distribution, just generate something, but then I have no access to which weights. I mean, I don't have access for doing the differentiation so that I can update the weights here if the encoding was not good. So there is this. These are the things that are there. But then let us go with this, and then we will put things in place. Everything, all the details will appear. So let us go step by step. So the first thing is to tackle this. So KL divergence, can I write an explicit form for KL divergence? And we can do that. So KL between Gaussians. So given Q phi z given x and Pz are all factored Gaussian distributions, KL term in, let us say this equation is D. So in my notes I use a D, so let us use this D as well. KL term in D has analytic form so what I claim is the following is KL Q phi z given x, and this is equal to half of mu phi of x minus 2 log of sigma phi x minus d. So what we are saying here is that the KL divergence that we have, which is the second term in the equation D, has an explicit form like this. Okay. So here we don't have to do any approximation here. We have an explicit form that we can derive. Okay. So let us derive this. It's just basically we have to remember the Gaussians and KL between the Gaussians. So proof. Okay. So I may take another 1 hour. So I will complete the VI today. Okay. So assume two factor distributions let us say Pz is probability of Pzi I equal 1 to d, and Qz is Qzi I equal 1 to d. So then the KL divergence between Qz and Pz, okay, is expectation of Qz log of Qzi I equal 1 to d divided by I equal 1 to d Pzi. Okay. So this is factor distribution. So basically factor distribution means that if I am computing for the z, then it's just product of the PDF values on z. So okay, so we have just kind of use the KL divergence definition. So this is expectation over Qz of log of Qz by Pz. Okay. So then this implies and this is equal to, so basically because of the log the product will become the sum. So this is expectation of Qz and then sum of log of Qzi by Pzi I equal 1 to d. Okay. So basically products became sum, okay, because of the log. Now sum can be taken out because expectation is a linear function. So sum is taken out in the next step. So I equal 1 to d expectation of Q of Zi log of Q of Zi by P of Zi, and this is sum of 1 to d KL. So basically it became individually KL, okay, for each I. Okay, so so basically now, since each of the Q are normal distributions with mean, let's say mu I and variance sigma I square, we will substitute these values. So what we have done so far is we are calculating the KL divergence between Q phi and P. Q is a product distribution, phi P is a product distribution, and so on. Right. So now we will assume that this Q and P are standard normal, not standard normal, I mean normal. So with mean mu and sigma I as the variance. So if we do that, then so assuming Q of Zi and P of Zi distributions are Gaussians. So Q of Zi is normal of Zi mu I sigma squared, and P of Zi is normal of Zi 0 1. Okay, so these are the choices we have, and as you can remember from the diagram, P that we had, right, we want this Z to have the standard normal, so that's why we have 0 1, and QZI that we are computing, basically it's QZI given X, we are dropping that. So the QZI that we are computing, it has the mean mu I and variance sigma I square. So we will put this in the KL divergence computation. So this is KL of QZI given PZI. So this is expectation of QZI, and log of 1 by square root of 2 pi sigma I sigma I don't know why I wrote square here, it was sigma I think, and then exponential of minus 1 by 2 sigma I squared Zi minus mu I squared. So this is for the QZI, right? So QZI, I wrote the PDF, which is 1 by 2 pi sigma I exponential minus 1 by 2 sigma I square Zi minus mu I, and then I will do it for the PZI, which is a standard normal. So here it will be a little bit simpler here. So 1 by square root of 2 pi, because sigma is 1, and then exponential of minus half Zi squared. Okay, so we have substituted QZI PDF, we have substituted PZI PDF, and now 1 by square root of 2 pi will get cancelled, and we will do some rearrangements, and if we do that, then we get minus log sigma I minus 1 by 2 sigma I squared Zi minus mu I squared plus half, I believe, Zi squared, and let us call this E. Okay, so we did the simple kind of so log and exponential got cancelled, and then minus log of sigma I came because of this guy. Log of sigma I didn't cancel, only 1 by square root of 2 pi cancel. So we have log of 1 by sigma I, that became minus log sigma I. Log and exponential got cancelled, so I got minus 1 by 2 sigma I Zi minus mu I square, minus 1 by 2 sigma I square Zi minus mu I square. So that term came, and then this was log of the negative of this, so became positive. So this becomes log and exponential got cancelled, and half of Zi square came from there. Okay, so this is Now the first term log sigma I has no random variable, so if I compute expectation, then this will be just the same thing because it's a constant with respect to this. But expectation zi is here, so expectation will be applied here. So this will be equal to minus log sigma I minus, it will be minus half, because expectation of zi minus ui, but whose distribution is qzi, right? So this is exactly the variance, right? So expectation of this guy is exactly sigma I, because variance is defined to be expectation of z minus mu whole squared. Okay, so that becomes sigma I square gets cancelled. So eventually we get minus half. And then at the last also we have sigma I, which will be, I believe, sigma I yeah, minus half, and then half. Okay, there is one more term missing somewhere. How did I miss this? Okay, so E is this minus log sigma I 1 by this, and then I have one additional residual term which is plus half of, but I don't see why it's, I don't see why it should show up. Minus log sigma I, that's fine, minus half plus half, sigma I. Oh, okay, I think maybe I did some mistake in my notes, but if I see this, then what do I have? Minus half plus I mean, certainly the second one is mu I squared, and then this is half. Okay, but what is missing is sigma I squared. Yes, because if you see in the claim, we have a norm of sigma I square, so we are looking for sigma I square as well. Log of sigma we have already, that's separated out, so somewhere we have missed. Okay, let's see from the start. So we have KL divergence of q zi p zi, and we computed the expectation. That's fine. And then we had expectation of minus log sigma I minus 1 by sigma I square zi whole square plus half sigma I square. That's fine. Then we had minus log sigma I minus 1 by 2 sigma I zi, expectation of zi minus mu I whole square. And then I have, let me see if I made some errors from somewhere. I had this one notes that I, okay, it is interesting. It is interesting that we do some changes here, okay, which means that we bring in, we deliberately bring in sigma I square by adding and subtracting sigma I with zi. So zi square is written as zi plus sigma I minus sigma I whole thing squared, and then it's expanded, and so let us do this. So we have minus log sigma I, and this is half is clear. So until here it's clear. Now expectation goes there as the last step, but here there is some trick done that I have kind of missed. So expectation of this applies here, so half comes out, and here I have zi squared. We say that okay, this zi square will be same as this, and now yes, like, so this will be the variance, and then this will be mu I square, then there will be one mu I square here. So this will be sigma I square plus mu I square, basically, because this, we are just trying to kind of do this derivation as well. So this is sigma I minus half plus half, and this is sigma I square plus mu I square. Okay. sigma I square plus mu I square. So we did this for the I, right? We have these results for I, but then if we do it for all, then we will basically vectorize these notations. So now if we do it for all, so writing using the vector mu phi x as the vector of means, which is mu d, and sigma phi x is sigma 1 sigma d. Okay, then we can write the K divergence term, which was sum, right? So which was sum of these. So we have so recall. Okay, so let me do this. Recall what we did from where we were doing this is qz pz, and then this became KL of qzi pzi. Okay, I equals 1 to d, and what we have done so far is we have done it for individual k of qzi pzi, but essentially now we are going to sum it. So if we are going to sum it, then we will get the norms of the means, because we have half of those, right? So sum we will do, then will be sum of sigma I square, sum of mu, sum of sigma I square will be the norm of mu phi x, which is defined to be the vector of all these mu, I mean this, and then for the variance also we have sigma phi, and half if we sum it d times, then this will be there is no half with d, right? But here we have half. So how did half go away, right? There is half. Okay, this half, is it like multiplied to all or yes, this half is like I did not close the bracket, right? So this half is applied to all. So now it makes sense. So it will be, if I sum half d times, because I'm supposed to do that, then I will get d minus half d, which I get there, and this term log sigma I have to sum it d times. So this is same thing as saying that I have to make a vector of log of sigma using this vector notation and then multiply it with vector of all ones. So that will make it sum of log of sigma I. And so that's what we did in the second last term there, before the d term, before the d. So essentially everything is in place. So as a last step, I will just write that sum, and then yeah. So we are done with this K divergence term, which is a closed form expression, and these closed form expressions have the parameters theta and all those can be used in gradient descent later on. So this implies KL of QZ PZ is equal to, now sum of these, as I said, this is like sum of these. So this is minus log of I equal 1 to d minus half, I mean I don't know how to write, so this is sum of half basically. So I equal 1 to d, and then plus half sum of I equal 1 to d sigma I square plus mu I square. So this can be written as this can be written as minus, let us put it outside, although let us put it outside, and then this is log of the vector of the phi, which is log of sigma phi x comma vector of all ones, minus half d plus half norm of sigma phi vector squared plus half mu phi x vector norm squared, and we can take a half common, and then everything falls in place. So if we do half, then we have, let us put the norm terms first. So this is norm of sigma phi x squared plus norm of mu phi x squared, and then we have the, let us put the log term then minus, so since half is taken common, so this is minus 2 log of sigma phi x 1, and then the last one will be minus d, and we close the parenthesis. So what we see from here is that KL divergence between the two distributions, which happen to be, the first one is normal distribution, and the second one is standard normal, and they have a closed form representation, meaning that there was no approximation anywhere. It's a formula expression that we can write, hence it's a closed form. So this is our KL divergence. Now let us go back to the first term that we had. So we had two terms in the L, right? So now we will focus on the second term. We have to estimate. So there's something called Monte Carlo estimate, which is nothing but just averaging over some samples. So that first term we need approximation. Okay. So now let us go back to that original term and see what we can do there. So this is Monte Carlo estimation. So VAE objective L phi theta, which we wrote there. So for completeness, we can kind of write like this, which was E q phi given x log of p theta x given z minus KL q phi given x p z. So the VAE objective, which is this, and all this is over the data. Okay, so expectation over the p data and so on. So what we have done so far is this guy. Okay, this is tractable. Given that Q is normal, P is normal, so we can do this. Now the first term in the VAE objective is still not tractable, and we have to do some approximation there. So we do this Monte Carlo estimation, which is simple actually. So via Monte, so this VAE objective, this is still intractable since the expectation calculation which is over the Q phi z given x requires evaluating the neural network transforms for all possible z, right? So for this, then we have to do some estimation, which we can write here. So using Monte Carlo, replace expectation of Q phi with Monte Carlo approximation, which is given as expectation of Q phi of z given x log of p theta x given z will be approximated via just log of p theta x given z, where z will be sampled from q phi z given x. Okay. So what this says is that in general, if you want to compute the expectation over the q, you will just approximate it via some for some samples basically. Okay, in this case it's like you sample q from this distribution, and then for these you do an approximate calculation. So basically it's when we do expectation calculations, we kind of want to do it over some samples. Okay, that's what, so we are trying to say, okay, I will generate some samples from qz given x, and then I will use that to calculate the estimate the probability value of log of p theta. All right. So and then we are also supposed to compute the gradient for the loss, right? Because that's how we will compute the we will modify the theta and phi parameters. So with respect to theta, if I have to compute the gradient of objective with respect to theta, and this could be estimated as L x phi theta, which is grad theta log of p theta x given z, and then z is sampled from q phi z given x. So again, if I have to compute the gradient of L, then I will compute gradient of with respect to theta for a given sample. So in this case, I do a sampling from q phi, and then for that z I compute the gradient. So these are the estimates we have. And now what about computing gradient with phi? Okay, so we have gradient computed with respect to theta, but we also need it for phi. So we can do it here. So to compute gradient, with respect to phi, grad phi L x phi theta will be approximated as grad phi expectation of q phi z given x log of p theta x given z, and then minus of grad phi kl q phi z given x pz. So if we look into the L term, right? So since we are going to do SGD, right? So for SGD we need gradient with respect to theta and phi. So if we look into the parameters involved, when I was doing gradient with respect to theta, then this has no role on theta. So that's why I never looked into this. So this is the first step. Okay. So I was just looking into how I compute gradient of this guy. Now I have to compute gradient of this guy, then I will do, based on the samples, I will do some approximations. Okay. So I will generate some samples from the distributions q phi z given x, and for those samples I will estimate the gradient. That's what Monte Carlo estimation means. For any given quantity, you based on the sample you estimate. Okay. So because samples is something I can generate, although it may be very continuous distribution and so on. But then I can generate some sample over which I can estimate. Although that's why I'm not saying equal, right? I'm saying that this is approximately equal to this. So and similarly, if I go to the phi, now in phi there are it's in both
the terms. So hence I have to compute gradient with respect to phi here as well as here. So that's what we have written there. So for the moment it's just symbolic right now. So we have done grad phi of the first term, and then we have done grad phi of the second term. Now good thing about the second term is that KL is a closed expression. So you can differentiate with respect to phi, because if you remember the KL term, then you had this norm of mu phi squared, norm of sigma phi squared, all are differentiable. Norm of inner product of log phi, I believe that was differentiable. So second term we are not really worried. Okay, so we can say that this guy is tractable because it has closed form solution. But then for the first term again we will do similar Monte Carlo estimates, and so similarly here also it's the same thing like we did for this. I will, for the first term again we will do the Monte Carlo estimate, meaning MC estimate, meaning sample sum. So what is the notation I use? Z. Okay, so sample, yeah, so sample Z from, in fact this is what we have done, but it's with the phi now. So sample Z from Q phi Z given X, and then compute the gradient of with respect to phi of the term log of, yeah, so P theta X given Z. So if you see the picture right now, it is essentially saying that you backprop here, okay, in the encoder. So VAE is a little bit tricky model, okay, but with all this notation so on, but no problem. Like let's say this is our phi and this is our theta, okay. So if I am computing gradient with phi is with the encoder, right? So and the Z that I am getting are the Z that comes from this phi, okay. So when I'm computing, when I'm sampling Z, okay, that's a mapping that I have from some phi function is producing the Z. So then I can go back and modify the parameters phi here, okay. So okay, so what is the situation right now? The situation right now is that VAE has this objective, and the first objective is the encoder, okay. So no, sorry, this is the decoder, and this is the encoder. So given an X, we generate this Z, okay, and we are supposed to compute the gradients obviously, because we have to kind of maximize this with respect to phi and theta. So so while computing the gradients, gradient of this guy is possible with because phi is involved here, but then it has a closed form solution, so we can do that. We know the expressions and we can compute the gradient there. So I mean computing gradient with theta will be just involving this term, okay, which we do the Monte Carlo estimate again. We sample Z from this distribution. And what is this distribution? This distribution is being created by this encoder here, okay. So from here I can sample basically many Z from there, and based on that I can calculate these gradient values I can calculate. So I will review this again from time to time, okay, because this is the nature of this model, is that it requires a lot of reminding of things. So okay, so what we have in hand, let us see. Okay, what we have in hand is we were given an optimization model and we were supposed to maximize. While maximizing, we have to take gradients, and gradients can be computed in this way, okay. Now I will come back to this again, like so okay, that's fine. So but what will happen is the following. The thing that I wrote there if you see Z is being computed from phi, so from is being sampled from Q phi Z given X. Okay, so basically what is happening here is that there is a distribution that I am trying to learn, which is Z given X, and this is coming from phi. Okay, so this is coming from phi. Now that is where reparameterization trick is coming. So if we don't involve the standard normal, okay, so if I sample from here, let's say, okay, if I sample from, let us say you learned a distribution and this is Q phi Z given X. If you sample from here, that sampling process, if it's not a differentiable process, you have no way to go and update this guy, because until here you got this, but after this you are sampling, because you need to sample from these to do this Monte Carlo estimates. But if your sampling process is a way that's not a differentiable way, okay, let us say arbitrary sampling process is used, then you have no way to go back and tell the network that the phi that you are doing is a bad one. Okay, you kind of like update your phi and so on. Okay, so that's where reparameterization trick comes in, that allows this mapping sampling process in a way that I can access the parameters of the model. So maybe it's still not very clear, so let me do this now, the so-called reparameterization trick. So the point here is, the problem here is that this sampling can be a sampling which is which you cannot go back and modify the parameters. Okay, I hope I'm trying to, what I'm trying to say is clear, but anyway, like I will keep reminding from time to time, and then so what I will do next is something called reparameterization. The whole point of reparameterization is not just sampling, but I want to go inside and take derivatives. Okay, so let us do that. So what is to be done next is, so we have used this several times, right? So Z given X, Z given X, we are saying each time, right? Z given X, Z given X, I mean sample Z, all the time we are saying this, right? For sampling, Z is good without sampling. Z is good while I am I won't be bothered, I believe, when sampling is done in a stochastic way here, because here I am worried about the theta. Okay, so theta I can change, because theta is coming after the Z. Okay, so theta. So again, I think it's always good to keep this picture a small one, even if it's a small one. It's good to keep this picture, because this picture helps a lot. So theta is here, phi is here. Now we need this samples, right? Z given X. So while computing few things, I need this Z Q phi Z given X, because these are the samples. Based on this, I am going to do the estimation. So when I am going there and I am generating some data, let us say X and X cap and so on, then I can modify the parameters theta here. Okay, but if I look at this gradient with respect to theta, it's only involved in this part. Okay, it does not look here. But when I am looking at the gradient with respect to phi, then it's like all the way here. Then if I have to question the encoder that you are doing badly with the generation of the distribution, then I need a way to go there. Okay, if these samples were generated as a stochastic simulation, in the sense that that I don't really know, I mean, a way to kind of differentiate that expression back, then I'm not I'm not able to kind of fix this phi that I need in general, and this phi that you need will be also accessed by the KL divergence, which will kind of regulate this Q phi and match it with the standard normal, which is PZ. Okay, so you can watch these videos again and again what I'm saying if it's going. So and so what I'm trying to say next is that the first term, grad phi E Q phi, still I mean what I'm going to say is the other one. Okay, so I think yeah, so our focus is here. This was okay, but this guy is where I will have an issue, because this guy I won't have an issue, because what I said is like I can work here it's okay, I can backprop here, but the cutoff point, the problematic point comes to be when I'm accessing this, and the access to this is completely cut off if this simulation, if this sampling was taken to be in stochastic sampling, which did not show me the mean and variance explicitly. Okay, so all this will come now. So okay, so okay, let me return. So first term requires grad phi. Okay, let me write this anyway. Requires this computation that we have, and requires this, which requires MC calculation, Monte Carlo approximation, and also sampling Z from Q phi Z given X is a stochastic simulation, does not give a way to compute gradient that is to do backpropagation. So computing gradient in neural network is called backpropagation. Okay, so computing gradient with phi, because it goes like this, because there is a algorithm called backprop to compute the gradient efficiently. It uses the chain rule. Okay, that's why it's called backprop. So do backprop. So for the moment, for us, it's not necessary to know. In fact, no, it's not necessary for us to know about neural network. It's not necessary to know about how the gradients are computed. For us, it's a black box. We can call Python routines, and it can do for us. Okay, so basically, it does not give a way to compute the gradient, especially with phi. Okay, so that's the problem. Okay, so then the authors of the 2014 paper introduced something called reparameterization trick. Okay, so introduce basically this trick is nothing but a push forward that I also mentioned briefly before. So basically what it says is that you sample Gaussians. So if I want to sample Z, which is let us say, which in our case all the distributions are assumed to be Gaussian. So in this case Q phi is a Gaussian, and then we can write Z as okay. So what I have done here is that let us say you sample Z. Okay, let us say we are here. the samples went in. When samples went in, some mean mu phi and some variance sigma was created. That's the probability model. X went in, mean mu and sigma phi was generated by the neural network. Two outputs were generated by the neural network, mu phi and sigma phi. Okay, and I know I force them to be a normal distribution, obviously. So with mean phi, mu and sigma phi, but then if I have, even if this distribution is with mu phi and sigma phi, if I just do some kind of like a random sampling out of this, I don't see this phi when I do these random sampling. But if I write like this, if I see z like this, which is mu phi plus sigma phi, and then like pointwise product with the epsilon, where epsilon is coming from standard normal. So standard normal with mean 0 and variance I, then this exposes the mu phi and sigma phi. Okay, so if I, rather than doing sampling in a stochastic way, if I see the sampling in this way, now when I am doing the gradient with phi, I have a handle on this phi, which these guys were created here after going through these transforms. So these outputs were created mu phi and sigma phi. Now with this reparameterization trick, I can go in, because this mu phi and sigma phi is now accessible. Okay, so it's accessible, and hence these phi parameters can be differentiated. Okay, with phi, and because what will happen in general is that you will have some samples. It will create some mu phi and sigma phi. Initially, this mu phi and sigma phi may be garbage, basically, in the sense that because this phi parameter of the neural network will be initially bad. Okay, but it will be some random, because I don't know that, right? So initially this phi parameter will be something random. So the distribution that it will try to learn for the normal will be bad one, because it's parameterized by, right now it's parameterized by phi, which has not yet learned in a proper way how to map distributions in a correct way. So and not just that, for the VAE, these mu phi and sigma phi that we are generating, the KL divergence is telling us that the mu phi and sigma phi that we are generating from this must match the standard normal. Okay, so what we are trying to say to the network is that you generate, but you generate this mu phi and try to learn to generate mu phi and sigma phi in a way that it becomes standard normal. Okay, now to teach the network that your parameter should be such that the output you are giving me will be, the mu and sigma will correspond to the standard normal. To teach that, I need an access to this. I need a way to modify the phi, and to be able to modify the phi, I need to know if the z was sample, then it exposes this mu phi and sigma phi, because mu phi is now I can see this mu phi as some neural network function which was applied on x with the parameter theta, and this gave me mu phi. Now that I am not happy with the mu phi, then I will go here and say that, okay, you do gradient descent, or in this case ascent. Okay, so because it's a max problem, let's say, so you do gradient descent or ascent, whatever is the loss function, and then you will say you tune your phi, because I'm not happy that your phi or mu are still very far away from the pz, which is standard normal. So you go back and please kind of like tune your model in a way that next time, if the next samples comes, I will verify again that whether you have learned to produce the mu phi and sigma phi which are standard normal or not. So that's the way to teach how the cat distributions are forced to become standard normal. But then how will you wing the variations, right? Because if I say that just exactly become standard normal, that's also bad, because I am building a generative modeling. So I need a way to also play with some variations here. So here, I mean, I need a way, kind of like the whatever this mu phi and sigma phi is coming, I see them as a translations and scaling of the standard normal. So this epsilon parameter is showing up here, and this epsilon parameter, since it's and it's not destroying the mean and the phi that came via this way. It is not supposed to do. Okay, it is not supposed to do, because then you will lose the information, right? So it preserves the information that the mu phi and sigma phi that came is the same mu phi and sigma phi, but then yet I am sampling epsilon from the standard normal. Okay, so the next time when I am generating the model, then this because I know that these guys are going to be standard normal anyway, so then in the next time, if everything is learned, meaning this ultimately our goal is to learn theta. Okay, but then we are also forcing the distribution to become like standard normal, because standard normal is the one which I know I how to sample. Okay, now to make it learn the standard normal, I need to be able to go back and allow change of this. So all these ideas are coming together. That's why this is a very like interesting model. Okay, there are like I mean, you need a way to keep variations, okay, but then you also need a way to have a known distribution, which in this case is standard normal, and you need a way to be able to tune the models of your network, which is phi, and for that we need this reparameterization trick. So for the moment, like I'm trying to say too many things at a time. So for the moment, our problem was taking derivative with the phi. Okay, if you see until here, then there is nothing much, because this gradient will stop here itself. Okay, but if I have to access this, I needed a way to go there. Okay, so that's called reparameterization trick. So for instance, I will do the sampling, okay, and then with this samplings, gradients will be computed and so on, and then the cost will be computed later on, and then I will see the cost is bad, and then I will go and tell the network that the jet that you were producing are not good, because the reconstructions I am doing are also not good. So you go back and learn a proper way to sample again, and the way you will learn to do a better sampling is by tuning your phi and phi parameters of the network. Okay, so I may be repeating multiple times, but these are the ideas involved here. So with this, now I can make it precise, the gradient with respect to the phi. So let us see what it means. Okay, because when you see this guy here, you will say, where is the phi here, right? You will say that it looks to me like as if this term, there is a theta here, but it looks like it's a constant with respect to phi, so I should get 0 here, but it's not that, right? Because we have not exposed the Z yet, right? Because Z is where the phi is hidden, right? So there is a dependence of Z on phi, which is in our case is mu phi plus sigma phi epsilon. So this is where Z is hidden there, and that is where the gradient will be applied in the sampling process itself. So then in that case, so let us use pi to define a pi of epsilon to denote and then we denote the transformation T phi as x epsilon, which is mu phi plus sigma phi epsilon, and then by lotus we have expectation of q phi z given x log of p theta x given z is expectation of pi epsilon log of p theta x given t phi x epsilon. So the whole reason why we expanded the z is to expose the fact that z is coming via a phi parameterized network. So that's why we use this additional notation now, that z stands for t phi x comma epsilon. Epsilon is taken from standard normal, and then the z is created via x going through the phi network, and then later on epsilon is injected, and then we get the z sampling from there. So this is how, like, this expectation is. So now if I have to take the gradient with respect to phi, now that gradient will be a little bit clear now. So gradient of phi, expectation of q phi z given x log of p theta x given z is expectation of pi epsilon grad phi log of p theta x, p theta of x given t phi x epsilon. So basically this is what this is how the gradient will go inside, and this is how the gradients will be computed. And now we will use Monte Carlo estimation again, because expectation we will compute it on some samples. So let us say there are m samples, let us say there are m images of cats we are trying to send. So these samples are the what you use to estimate, okay, these expectations. So let us say I have to do let us say I build this the whole KL divergence, the whole loss of the VAE. Then we can write down the whole thing now. So we can write down, so with mini batching means batch of inputs, okay, and Monte Carlo estimation. So we can write down the way we can actually compute these things, okay. So in computationally how we can do this. So this is log of p theta xm t phi xm epsilon m, and then minus kl q phi zm xm, and then p of zm. And here these are samples m equal 1 to m. So let us say there are m samples that goes in. So your loss function now becomes this approximated over a sample, m samples, let us say, and and we know how to compute the gradients with phi, gradients with theta, okay. So here x1, x2, xm are samples, and epsilon 1, epsilon 2, epsilon m. So what we are expecting this network to do is to generate a distribution itself, okay. So here p theta of xm t phi xm epsilon m is chosen to be normal xm g theta zm sigma square identity. So what we are saying is that this p theta is also some template distribution, let us say normal, and this normal distribution is producing some mean after taking the ZM. So I believe, one second, I think I'm in a good shape to give you a full picture. Okay, so let me now tell you the full picture of what is happening with this figure so that we really understand. Okay, so let me draw a figure here and then okay, so there are three distributions involved here. Okay, so what are these three distributions? So one thing is when x goes in. Okay, now we can build a mini batching system where not just one image goes, a batch of images can go. Okay, so we can think of x1, x2, x3 and so on. Okay, so I think it is good to go with the batch. Yes, let us go with the batch so that multiple cat images are going in. Okay, now for each of them it goes through the encoder network which is phi. Okay, and this encoder network is forced to be a neural network. Encoder network is a neural network, but it's forced to be a distribution with mean and variance. So this is the first distribution. The first distribution is telling us is produce p z, and since we are using m, so let us say one of these small m, zm given xm, and this is following the normal distribution. So basically the network is producing each time these vectors and so on, means and this. And then the second distribution is so this is the first distribution, and the second distribution is p of z. Okay, so what I am expecting in practice is that I am expecting this p of zm. What I am getting in practice, what I am getting in general is zm given xm, but what I want in reality is that zm follows the standard normal. Okay, so the KL divergence will force this. So KL divergence will tell that you better be equal. So KL divergence does this by doing a measure of this p zm given xm and p zm. Okay, that's the term that you see here, and these are the phi. These are phi. I think now what we have is we use the notation q here. Sorry. Okay, so this we use q, and okay, so we are trying to learn the working process of VAE. So samples goes in. Samples are forced to be producing two parameters which are mu and sigma, and these two parameters are forced to be equal to the standard normal, and that is via the KL divergence is trying to do that. If not, then this cost will be very high, and the gradient descent will come back and say that I see that the distributions we are producing is very high, so let us go back and kind of update the parameters phi here. Okay, so that's the change in the weights of the phi also comes via KL divergence. Okay, so what do we have now? So now we do this process repeatedly, right? So x1 goes in, x2 goes in, and so on. Okay, and we build an estimation of the distribution with mean mu and sigma variance, and so then what we get is some Zm that follows this mu phi and sigma phi. Okay. So one possibility is that we let it just let it just produce these two parameters, and I say that these two parameters correspond to the mean and the variance, and then the next step I can say that I will let me just sample from there. Okay. So the fact that this is close to the fact that this will be close to the standard normal will be kind of forced by KL divergence itself. Okay, KL divergence is there to say that okay, you're far from here. You're far from the normal distribution. So then comes the reparameterization trick that we did just now. That says that Zm, let us expose this by doing mu phi plus sigma phi, and then epsilon, where epsilon from standard normal. So the reparameterization trick carefully exposes mu phi and sigma phi while keeping it close to, because the KL divergence will force it to be standard normal. The fact that I'm keeping standard normal is like saying that if KL is forcing these guys to be 0 and 1, then I'm not disturbing that anyway, because I am taking from standard normal. So if your mean was already 0, variance of 1, so if with this I still keep it 0 and 1, so I will not contradict that. So that's what it means. So essentially, but then rather than doing this stochastic sampling where you don't have a view of these mu and sigma, here I have a view. So once I see this, then if KL divergence tells me that the mean and the variance you are producing this way is not as good, is very far from this, then via this I will go back to this network and say, okay, you did bad because the KL divergence is telling me that you did bad because you are very far from the standard normal mean and variance. Go back and change your theta. So next time you will do gradient descent. So next time it will have an updated phi tilde, and I mean ideally for the sample that you started with, now the cost should be decreasing. Okay, but so next time it has updated its parameter because it's trying to learn that I made a mistake because the sampling is not good. So then next time it will try to generate better. This is the part of supervised learning, right? You train the network like that, right? So cost function is like a teacher in some sense. Okay, it's telling you that okay, go back and change your parameter and do well next time. So here it goes here with the next phi tilde network. You expect that the mu and sigma that is produced, even if for the next samples, okay, will be closer to 0, 1. Okay, if it is still far from 0, 1, KL divergence will say, oh, you are doing bad. You go back and learn this again. Okay, so and all this is happening because of the reparameterization trick, because this is allowing me to access mu phi sigma phi, and the next time I will sample Z, it will be mu phi tilde sigma phi tilde and so on. Okay, so this is the sampling part, right? So where we are forcing the input to be closer to the standard normal, and we are doing it because standard normal is something we know how to sample, and from that sample I want to generate the realistic image back. Okay, because the next time if I have to generate, I will forget this guy. Okay, I will forget this guy because this guy has learned how to generate images from standard normal. Okay, the whole process in training involves encoder and decoder, but then during generation I just need decoder because I will leave this I know that this network has learned how to sample these images from the standard normal. Okay. Okay, so now let us focus here. What is happening here? Okay, so here now what goes here are ZMs, right? So these ZMs that you are producing here, and this encoder also has to learn, right? This encoder has to learn to produce the images that were fed here. So they cannot be initially, they cannot be decoupled, right? So ZM are the samples being generated from here, but this network has to figure out how to transform these samples to the original image back. Okay, so let us say this is X hat. Now here, so here comes the third probability distribution here. So we had the first one, encoder probability distribution or normal distribution, standard normal distribution, and then the third one is also normal distribution. So that we call it P theta XM. Okay, so we call it P theta. So originally we wrote it like XM ZM, but later we wanted to expose that ZM is coming from phi dependence on phi XM epsilon m and so on. Okay, so let us focus here. So this we call it, this we say that now you should produce yeah, so we say that this distribution will be standard normal and it will produce mean to be like this and variance to be like that. So there is one last step which I believe will take maybe 10-15 minutes only, that will relate to how come this is going to be approximation this. So this is not yet clear to us. What we are saying is that this is going to be a distribution with mean this, but a natural intuition behind, a natural intuition that you may have right now is that it should have the same mean that these xi's had, because that will exactly be the meaning of a correct reconstruction, right? So if this x1 to xm went in through some process, it went through this intermediate step, bottleneck step where you have this normal distribution and so on, but then what comes after this, you are expecting that the mean of these guys will be the distribution that is learned here will give back will be the distribution whose means are the same as the original cat images, because if it learns to do that, then I know that it has learned, the encoder has learned to produce the distributions that corresponds to the cat image. Okay, so that's the that is the step, the last step in this. Okay, so so what I want to show you is that this indeed corresponds to kind of like having this mean. So writing this term as a last step. So I am forcing this to be this, right? With mean this. So let us do this step. So if it is normal, then it is 1 by square root of 2 pi sigma e to the minus xm minus g theta zm squared by 2 sigma squared. So since I am forcing that this is supposed to be this is supposed to be normal, then its PDF will look like this. Now if I now look into the cost with this expression for p theta, so if we write the L phi theta now, so with this L phi theta is 1 by m sum of log of 1 by square root of 2 pi sigma e to the minus xm minus g theta zm whole square by 2 sigma square, and this is whole log, and this is m equal 1 to m, and this is equal to, so I will take few things common without may not be precise exactly, but you know that these are constant terms are not that important right now. So this is, so basically I split the log m equal 1 to m plus, and the term that I have in the log is minus of x1 minus g theta z1 squared by 2 sigma square plus minus of x2 minus g theta z2 squared by 2 sigma square, and so on. So as you can see, if I look into the loss, I'm not loss, I mean I have written this, yeah, I mean let's say the loss, but the only the this corresponds to the first term of the loss. Okay, so it has to be a little bit clear that this was just the first term, first. So just look at the first term, okay, because we know that we had more terms, right? Because this was just the first term, right? In the loss, we had KL divergence also. I mean, but KL divergence we don't worry about because KL divergence has closed form representation right now. But what we want to know is what does this do, right? So, so if we look into this, then since there was a log term involved and so on, but then we went away with this, and we can take this as a constant. So this is constant plus okay, this minus actually minus 1 by 2 sigma square, and I can take this as norm of x minus g theta z. So you see the effect of this, right? So if we have L theta phi, and if I force it to be a normal distribution, then the L theta phi boils down to this, the first term, and this first term is telling you that that x must be close to g theta z. So g theta z is something being produced from here, and what this tells me is that the x that went here from here, x must be close to this, because I'm trying to maximize L theta of this. So then I'm supposed to minimize, because that's in the negative. So I am supposed to minimize norm of x minus g theta z. So basically I'm saying that x should be close to g theta z. Okay, and but if you see it in terms of probability, then what it says is that the mean that is being created for the z, so the zm that goes here, okay, and the zm that goes here, and then the g theta of zm that we create is the mean of the xi's xm. Okay, but then all this corresponds to an equivalent statement saying that x will be close to g theta z. Okay, so that's the variational autoencoder where we do the encoding and then the decoding. Decoding phase also involves probability distributions, but then those probability probabilistic model, and then those is equivalent to saying that we retrieve the original image, okay, back. So, and when you have to do the generation, then you forget this, okay, because while doing all this process, you will make sure that the generator is very good, because it has learned how to produce from z, which is coming from standard normal, and it will become standard normal because KL divergence will force it to be standard normal. And once it runs from the standard normal, then you know that z eventually becomes standard normal, and from standard normal you can sample, and from sample you can start generating realistic images. So that's the whole idea behind VAE. We can discuss a little bit more, but someone is waiting, so we can stop for today, but more or less we are done with VAE. Okay, so okay, thanks.